Hi everyone, thank you for joining today's webinars. My name is Chinh Nguyen. I'm Technical Application Specialist of Dolomite. So in this webinar, we will be talking about the optimization of lipid nanoparticles formulation using a microfluidic technology paired with the automation. So the content of today's webinar will be including the introduction of the Dolomite team and the introduction about the production of lipid nanoparticles. And after that, we move to the introduction and demonstration with Automated Nanoparticle System and control synthesis of lipid nanoparticles. Finally, we move to the conclusion and the Q&A section. So during the webinars or presentation, so if you have any question, feel free to write out the question in the question box. So I will directly answer the question in the Q&A section. Thank you. So the Dolomite team is a team of chemists and engineers with a focus to produce high-performance micro platform allowing precisely controls over size, shape, and structure of particles. So we focus on a broad range of applications spanning over various industries, not limited but including the biomedical and pharmaceutical industries. We also supply standard products, for example, like particles, specialist chemicals, and emulsion stabilizers. We also advise the customer on microfluidic setup and processes, and if required, we can do the proof of principles project for customers before going to equipment purchasing. For lipid nanoparticle productions in the past, the lipid nanoparticles were generated through laborious and unreliable process, which includes, for example, like thin film dehydration, solvent dispersion, or membrane extrusion. So the process or methods have many challenges, like there's no advanced formulation screening platform, or no off-the-shelf formulation solution, or no IND-scale robust platform for lipid nanoparticle production, and it's difficult to control technologies for developing formulation, and also there's no automation existing platform. Recently, microfluidic synthesis is a favorite for manufacturing lipid nanoparticles because it brings many advantages using the microfluidic techniques. For example, like it can bring the high encapsulation efficiency with excellent monodispersity, showing at low polydisper index. Also, the process is reversible and continuous flow process with low material consumption for screening, and it can be easy to scale up. So for making the lipid nanoparticles using microfluidic technology, the lipid nanoparticles will be formed using a process of nucleation and growth. So the lipids will be dissolved in the solvent, for example, like ethanol or isopropanol, and is hydrodynamically flow focused in to the chip by the anti-solvent like waters or the buffers. So the nanoparticles will begin to assemble as a result of mixing, and it will be believed to be formed at the interface of the two streams between the lipid in ethanol and water phase. To control the size of the particles, we can control the flow rate ratio or total flow rate. The flow rate ratio is determined by the water flow rate divided to ethanol flow rate, or reverse way, like ethanol organic flow rate divided to water flow rate. So for encapsulation process, the encapsulant or API can be brought in both continuous phase in terms of the API is hydrophilic, or interface in terms of the API is hydrophobic, or it can be encapsulated afterward through the active loading method. So for the ultimate protocol development, there are many interacting variables and reagents to optimize when making a lipid nanoparticles. If you have a look at the graph, we have 3 different stages when making a lipid nanoparticle. The first thing is the discovery stage that we need to do screening process, and after that we move to development stage that covering the optimization, and finally is the production stage for numbering the production product. So for development stage, the materials are scarce and very expensive, so people therefore need automation system which work with small amount of materials. This is the ANPS Automated Nanoparticle System. So we have launched the first our new range system that allows protocol and development and production of lipid nanoparticles. The system will be including the pressure input store, so it can be stored reagent under pressure up to 1000 millibars that have to delivering material or velocity volatile compound reagent into the microfluidic chip during the process. And the ultimate sample barrel will include into 2 independent sample loop and 2 automated sample barrels. So it is for delivering small amount of the materials for protocol development process. The system including the 2 microfluidic pump, we have 4 independent channels that allow customer can delivering the maximum 4 fluid into the process. And finally, is automated collectors. We can be automatically collect the sample after running the experiment. So the system using the microfluidic chip for formulation of nanoparticles with a different geometry depending on the target application of the customers. So it will affect different chip type with effect on formulation process, for example, like particle size or encapsulation efficiencies or production rate. For system operation, the nanoparticles will be loaded in separate sample. We have optional 1 milliliter, 5 milliliter, or 10 milliliters together with the system in an ultimate unit ASVs. So they are manually inject and enough the particles, nanoparticle precursor for several experiments can be loaded into 1 go. And the high performance of the pump will feed nanoparticle precursors from the sample loop through the microfluidic chip into the collection unit. So this system will design to ensure all of the precursors will meet at the correct timing, and collection barrels will allow the samples to be accurately captured with the optional haircut and at the center part of sample. So the samples will be collected in series of the wires without manual intervention by using the automated collection samples. And between the repeat experiment, the fluidic pathway is worked before commencing the next collection to prevent any contamination during the process. This graph showing how the system works. Basically, you can see we use three different string channels in Qualcomm to different of the precursor into the microfluidic chip. So the first string channels, we will be delivering the nano precursor 1 into the microfluidic chip at the continuous phase, and the microfluidic 2 will be used for nanoparticles precursor 2 injections into the microfluidic chip as the interface. So the nanoparticle will be formed at the first chip, and the products after going out from the first chip will go to the second chip for optional dilution process. So the first pump will driving the dissolvent for the dilution and to be diluted, the product will be diluted at the T junction of the second microfluidic chip, and after that it will pass through collection valve to be collect sample by automated collected sample module. This slide showing the software using for controlling the ANP system. So we use the new version of the Flow Control Center FCC with the protocol editors. So the customer can say protocol for multiple user, or making a different protocol for running experiments. The fluidic pathway is generally fixed to up to 3 inputs, as we use the 3 input drop reduction chip along with as standard with the system. However, it can be flexible for using the different chip with the system. And the user can easily set up a list of experiments by changing the flow rate ratio, total flow rate, and sample size in the protocols, the data system, the data, and the system will be calculate on a reagent volume required. In the software, if you have, you can see it have a device tab that showing all the device module or modules in with inputting the system. So it can be manually controlled each device, and it works in continuous mode for production. So all of the results can be exported and import or export experiment created offline in Excel. So in the protocols data editor, we can inject, we can input the flow rate, nanoparticle flow rate of nano precursor 1, or flow rate of nano precursor 2. In terms of you need to change the relative flow rate ratios. You can input a different value of the flow rate, nanoparticle 1 and precursor 1 or precursor 2. And the flow rate of dilution is optional in terms if you want to dilute the product after formulation. This one will be input of the volume of nano precursor 1 if you want to do it in one experiment, and system will automatically calculate the volume required for nano precursor 2, nanoparticle precursor 2 as well. And this is the haircut and tailcut optional. To have the customers in terms they want to obtain exactly precisely the products during the formulation process or each experiment. So this slide will show our records, the demonstration of the ANP system from our lab. So I hope that this video will play smoothly during these webinars. However, in terms of if you cannot play or you cannot get it smoothly in video and audio quality due to the connection, internet connection. So we post this video in the YouTube link, and please refer in the chat box for the link so you can watch this video demonstration right after the webinar finished.
Here at Dolomite Microfluidics, we've been using microfluidic technology to produce micro and nanoparticles for over 15 years. Our systems enable researchers in both academic and industrial settings to produce particles with a level of control unattainable using typical batch processing methods. When choosing equipment to develop, screen and manufacture particle formulations, factors such as usability, experimental consistency and precision parameter control are all key to ensuring the level of particle quality required for your applications. And automating these experiments, that's even better. My name's Ben Nappett, and I'm Head of Science and Applications here at Dolomite Microfluidics. My background is in particle synthesis and characterization, so my team and I understand the importance of particle size, dispersity, and efficient use of costly materials when optimizing your desired particle performance characteristics, such as encapsulation efficiency or API release profile. These characteristics are vital for applications such as API delivery and release, or for targeted therapeutic treatments. To facilitate our customers' work in these areas, I'm pleased to introduce the Automated Nanoparticle System by Dolomite Microfluidics. The system features two Dolomite quad pumps, each of which holds two pairs of syringes that aspirate and dispense the driving fluid held here in the bottles of the pressurized input store. The driving fluid primes the fluidic pathway, including the sample loops in the automated sample valve, the droplet chips, and finally the automated collector. When running your protocol, the Flow Control Center software prompts you to load your nanoparticle precursors. Samples are loaded here at the ASV via two different syringes that fit into the lure fittings on the front of the valves. During a run, the ASV releases the defined volume of your nanoparticle precursor from each loop to converge in the microfluidic chip. Once the two fluids have converged, a downstream T-junction chip allows further optional dilution of your sample. Your fluid packet then travels to the automated collector, where the automated valve allows the collection of your sample into vials. The type of rack can also be altered according to your desired collected sample volumes, and that includes using a 96 well plate. The system is designed for, but not limited to, the production of nanoparticles, whether that be lipid or polymeric nanoparticles. In order to show you the system in action, my colleague Garinda will now give a demonstration.
Hi, my name is Garinda. I'm a Senior Application Scientist at Dolomite Microfluidics. Now let's begin some experiments. To start with, let me show you how to set up an experiment. To do this, we will use our Flow Control Center, which allows easy, user-friendly control over your hardware. You can navigate to the Devices tab, where you will find individual windows showing each of devices connected. So you can see the software recognizes 4 syringe pairs, 2 on each quad pump, 1 ASV and 1 automated collector. Each component can be controlled separately by the user in manual mode by clicking on any of these functions. Next, we are going to move to the Protocols tab. Here you will find apparatus window showing the devices corresponding to the function that's required. You can select the devices from the drop-down menu. The name of the device is dictated by your assigned label in the Devices tab. In the Parameters window, you can see that the user has the option to dilute their sample, and you can select either yes or no. The wash rate is the flow rate you want to use to wash the system in between experiments. The next 4 inputs are your volumes of your critical fluidic pathway, which allows the system to automate your sample convergence and collection. These can usually be found in the tubing kits which accompanies your hardware. The experimental tables also allow you to have full control over how you want to run your experiment. You can choose your flow rates for each nanoparticle precursor and the dilution step. You can define the volume of your nanoparticle precursor 1, and based on the flow rate ratio dictated by your flow rates of the system, automatically calculates the volume required for your nanoparticle precursor 2 and your dilution. The head and tail cut allows further precision of your collected sample by allowing you to collect a heart cut of your sample by removing the front, the head, or the back, tail end of your fluid packet during collection. This is an optional and customizable step where the user can determine the volume of the head and tail cut. I have pre-filled 4 experiments with different flow rate ratios ranging from 1:1 or 4:1 flow rate ratio. The total volume of the fluid packet is 1.5 milliliters. However, with 250 microliters of head and tail cuts, we will collect 1 ml sample for each experiment. You also have the option to set up your experiments offline in Excel. These buttons enable you to export or import CSV files directly into or out of your experimental table. When ready, click OK and start experiment. The output dialog box on the right here communicates to you what the system is doing at each stage, and this is automatically logged in your log file found in the Logs tab. When the system has finished priming and is ready for you to load your sample in the automated sample valve, it will prompt you with a pop-up on screen telling you the volume required for each loop. Your total execution time can also be monitored at the top. We're now ready to load our nanoparticle precursors. As we're running 4 different experiments, you will load the total amount of nanoparticle precursor required for all your experiments. The automated sample valve will gate your repeats in the sample loops, only releasing enough nanoparticle precursor to run 1 repeat at a time. For the purposes of this demo, I'm using 2 different food dyes, yellow and blue, as this will allow you to visualize them as they travel towards the chip. Let's load the samples. Once your nanoparticle precursors are loaded, you can simply walk away and let the system collect your samples for you. As you can see, the first experiment has begun. The dye, or your nanoparticle precursors, are now being released. They travel towards the chip where they converge. This is indicated by the color change to green. The sample now travels via the second chip where the user can add an optional inline dilution. However, in this case, we will bypass this step. The sample travels towards the automated collector where the first 250 microliters of the sample are sent to waste. The heart of the sample is then collected in the collection vial. And finally, the last 250 microliters of the sample is also sent to waste. This is to ensure only the center part of the sample is collected where no dispersion with the driving fluid has taken place. You now have your first collected sample ready. The system will now perform a wash. This happens automatically in between each experiment. Your fluidic pathway is washed with your driving fluid to ensure no residue from the previous experiment is present. You can choose your driving fluid depending on your formulation. The second experiment is now beginning. Once again, the dye is released at the ratio and the flow rate entered in your experimental table. The 2 dyes converge at the chip and are once again collected by the automated collector in the next vial. As the collection of the sample finishes, the system carries out another wash to prepare for the third experiment. This will carry on until all experiments in your table are complete. So overall, the system enables you to control flow rate ratio, total flow rate, and run various protocols to optimize your formulation, and finally run in continuous mode. Our glass microfluidic chips are reusable with a long lifespan. They can be cleaned in place with a chemical of your choice and can also withstand autoclaving. And that's all for today's demonstration. If you need any further information from us, drop us a message at dolomite-microfluidics.com. Thank you.
Okay, so I hope this demonstration video ANP system will help you to better understand about the automation system for lipid nanoparticle formulation. And next slide, we will move to the controlling synthesis of lipid nanoparticle by using the ANP system which pairs with the automation. So for making lipid nanoparticles, there's many variables that can affect to the synthesis process. So one is the formulation variables, which including the type lipid, concentration of lipids, and ratio of the lipids. The second variable is the chip type, thus including the mixing the region. And the third point is the flow rate ratio is the ratio between the organics and aqueous phase. And next is the variable is total flow rate, that is the combined total flow of the organic and aqueous phase. And finally is the volume. It including the nanoparticle precursor loading volume. And lipid nanoparticle size. Sorry. Okay. So sorry. So there's something wrong with the audio connection. So I will try to solve it. So the all the variables that will be respond in the 3 points in the results, like lipid nanoparticle size, the monodispersity, we saw it in the polydisper index, PDI numbers, and the encapsulation efficiencies. And what is important about lipid nanoparticles? The first important point is monodispersity. So the customer will try to get the as low as the PDI numbers, which normally is commonly less than 0.1 for nanoparticles, or less than 5% of the coefficient variation for microparticles. The second important point is the sign controls. So just wiring of targetable particle size more preferable. And the third one is the consistency from optimization to manufacture. So the requirement is the rapid optimization of particle synthesis during the R&D stage, and to find the optimized condition with minimal development required for pilot and manufacturing scale production for bulk production. And point number 4 is the encapsulation efficiency. So high direct loading, for example, like large, bigger than higher than 90% is more preferred, and with a minimal weight. And final important point is the control payload release. So it enables and decreases payload release over time. So here is some experiment data that we have done in our lab using the ANP system to do the optimization of lipid nanoparticles for the application. So the condition when we're running the experiment is lab, including we use the reagent organic phase with the phospholipid and DAB as a lipid source, and dissolved in ethanol. And the aqueous phase buffer and dilution phase also buffers, with the flow rate ratio variables changing with the experiment, and with under fixed a total flow rate at 3 ml per min. So if you have a look, this graph is showing the result of experiment when we change the flow rate ratio. So it shows the particle size, lipid nanoparticle size is controlled by variation of the flow rate ratio. So it means that it's very easy to control our lipid nanoparticle size using the system. And in the second results graph is showing the particle size and PDI numbers at the 3 different experiments that we repeat for fixed condition. So the result so is very consistent between the three different experiments. Yeah, it's so consistent in particle size and with good PDI numbers. So it means that we can achieve the reproducible results with the system with the target low PDI. So this slide showing the diverse data experiments we use for particle size distribution, particle size analysis with different three different repeating experiment system. So it's showing the very consistent data between the three repeating experiments. And next slide showing the consistencies can be maintained when we increase throughput. So in this experiment, we use the same experiment condition with the materials, and we faces with the two different flow rate ratio. And we're changing to total flow rate from 1 to 10 ml per minute, or 1 in first graph, and 1 to 15 ml per minute in second graph. So as you can see, the result showing the total flow rate doesn't affect much on the particle size and PDI numbers. So it means that we can increase throughput, but increasing the TFR with no compromise in reproducibility. And all of the PDI numbers also very consistent. So this experiment showing that we can increase the total flow rate to increase the throughput, and also it increase the experiment time. So it means that we can increase the cycle time. So it can easily to increase the library generation, means that you can do more experiment with less time when you increase the total flow rate. This slide showing the develop and produce lipid nanoparticles with a single system solution. So it's showing the results when we're running the experiment at protocol mode and continue mode with the same condition. The results showing that there's a very consistent when we running at protocol modes and at continuous modes. It means that the system can allow you to do the optimization process, and you can find the optimized condition for further bulk production. So you can use the parameters that you investigate during the development protocol and use for the scale-up production. So all of these show very consistent between protocol and continuous mode. So there's no compromise in lipid nanoparticle size or PDI shipping from protocol to continuous production. So it means that the ANP system is ideally for initially the production scale until you want to scale up the process. So yeah, the conclusion: the lipid nanoparticles are popular choice for target delivery of the biotherapeutic, and the microfluidic technology offers flexible and controls over lipid nanoparticles generation. And the ANP system offers a unique platform for optimization and continuous production of the lipid nanoparticles. So which resulting in lipid nanoparticles are reproducible and homogeneous. And finally, there are many factors can influence your final product. So technical factor can be easily controlled with the ANP system. So I finished my presentation here. So thank you for your attention. And now we will move into the Q&A session. So if you have any question, please write down your question in your question box or chat box. So I will directly try to answer all of your questions in the Q&A section. Thank you. So please write out your questions in the question box. In terms if you have any question. So you can visit to our website and visit to the Automated Nanoparticle System information, and you can download the application notes that we have made, and also the posters, scientific poster data for the applications about using the ANP system for making a lipid nanoparticle or PLJ nanoparticle as well. So please feel free to write out your question if you have questions, or send us the email to Hanoi office at blacktrade.com in case you have further question in next time. Okay, so it seems like there's no any questions at this moment. So if so, I would like to finish the webinar today. Thank you all for joining us today's webinar, and I hope that this is helpful for you, all of you, in your research by using the automation option in your protocol development when you're making lipid nanoparticles or the other nanoparticles. Thank you, everyone, and see you again in next our webinars. Thank you very much. Bye.